Morning, everybody. Before we get started on today's material, let's do a little review on the malonic ester synthesis and the acetoacetic ester synthesis. So it turns out that these so-called beta diesters like this are also known as derivatives of malonic acid. So these are malonic esters. And as you might expect, the hydrogens on the alpha carbon are unusually acidic because they're next to two carbonyls. And so we can deprotonate them quite easily with mild base. And so in the case of the malonic ester synthesis, you would use the salt of the alcohol that's used to make the ester. And that can undergo a reaction where you deprotonate one of those alpha hydrogens. So now we just have a single hydrogen there and a negative charge that's resonance delocalized. These molecules are actually fairly good nucleophiles, and they can be alkylated quite easily with alkyl halides, as long as they're primary alkyl halides. Secondary alkyl halides are a little more difficult, and tertiary, of course, don't work at all. You just get elimination chemistry. But for example, we can take these molecules and react them with something like iodomethane, do an SN2 reaction, and we've just made a carbon-carbon bond. And what's so important about the carbon-carbon bond? That's kind of the basis of everything we're talking about, right? Being able to take smaller molecules and make bigger molecules that we want. And there's only a handful of ways to do it. And the malonic ester synthesis is nothing more than a carbon nucleophile reacting with an electrophile. So it's really not a new reaction. It just has a different name associated with it so that you know what the starting material is. The neat thing about this, though, however, is that that remaining hydrogen is still acidic. So you can do a second alkylation with, first you would react that again with the alkoxide to deprotonate. And then I'm going to show you an example where we've actually done in my lab. That's just alkyl chloride, right? And so we're going to do the SN2 chemistry here. Methyl group, oxygen. And we've made molecules like that. Now, what we've been able to do in my lab, which is kind of interesting, at least to me, because we do it, is we use an enzyme known as pig liver esterase that will hydrolyze one of the esters and convert it into what? If I hydrolyze an ester, what's the product that I get? I'm going to get a carboxylic acid, right? So if I hydrolyze it, I'm going to get a carboxylic acid. But not only do I get a carboxylic acid, I get a chiral molecule. I go from this, which has no chiral center, but when I convert one of the esters to an acid, now I've got four different things around that carbon. I have a chiral center. If I were to do this under acid conditions or under basic conditions, I would get a racemic mixture. However, enzymes are chiral entities, and pig liver esterase can do this in water at approximately a pH of 7.0. If you take an ester and put it in neutral water, it doesn't hydrolyze very quickly. It takes years and years and years. The enzyme lowers that activation energy and allows this hydrolysis to occur. And then we take these and convert them into amino acids, but I'm not going to talk about that today. I'll talk about that when we get to the amino acids chapter. But the cool thing is that we do sophomore level organic chemistry 99% of the time in my laboratory to make the molecules that we use to feed to these enzymes to get the products that we want. Okay? So each and every one of you at this point could come in and be productive in the research lab making these types of molecules that we use every day. Okay? And so we have these chiral molecules that we then go on and do other things with using the pig liver esterase enzyme. You literally take a pig liver, grind it up, you got pig liver esterase. It's a pretty simple process. And it's able to convert esters into carboxylic acids quite easily and in a selective manner. Now, if you were to take this molecule and you heat it up a little bit, and this is where people get in trouble in my lab. They will take the molecule and they'll put it on the rotovap to remove the solvent, and they'll get in a hurry, and we've got a water bath under there to heat it, and they'll go, well, I'll just crank it up. And when they crank it up, it undergoes a different reaction. What kind of reaction happens at this point? It eliminates what? It eliminates carbon dioxide. It decarboxylates. And this happens somewhere around 50 or 60 degrees Fahrenheit for an ester. They decarboxylate pretty easily. So when we're trying to remove the solvent in the lab, we try to do this at room temperature below. But every now and then I get somebody that gets in a hurry. They want to go to lunch or they want to go home. They think, well, I'll crank it up. And then they crank it up and they get something that's absolutely useless. You get this, right? So what's the mechanism for this? How does this happen? Well, we need to draw the molecule just a little differently. And just allow me to abbreviate as R here, okay, so I don't have to draw everything out because it's not terribly important. How do I push the electrons? Okay. There are 6 electrons moving, and so what happens is and so you lose carbon dioxide that way. And what's the product, the immediate product? Let's see, R and the methyl group. What is that? It's an enol. And what are enols in equilibrium with? The keto form, right? In this case, it's not going to be a ketone, it's going to be an ester, right? And so this is in equilibrium with that. And which way does the equilibrium lie? To the product. That's right, so the ester. So it goes through an enol mechanism, eliminates carbon dioxide through this kind of like a 6-membered ring. You're pushing 6 electrons. This happens at about 55, 60 degrees, something like that. And so the cool thing about this, though, right, is that you can do malonic ester chemistry, and you can get to an ester that's now more substituted. And if that's what you want, this works really well. We want these products. But the malonic ester synthesis actually involves the decarboxylation of one of the carboxylate groups, and you end up with a new ester, okay? And ultimately, then we could take this ester, we could hydrolyze it, and we can get a carboxylic acid. So the malonic ester synthesis allows us to make higher substituted carboxylic acids pretty easily. There's another reaction called the acetoacetic ester synthesis, where you start off with a keto ester, and it's usually this ethyl ester that most people start with because it's dirt cheap. Okay? That looks kind of similar to the malonic ester in a way, except it's a ketone and an ester instead of 2 esters, right? So what do we know? We know that these hydrogens, again, are going to be extremely acidic, right? And so we can remove them in base. What base would you use here? I could technically use LDA. It's a little overkill here. I don't need anything that strong. THF? That's a solvent. I could use solvent. I would simply use sodium ethoxide. It's the salt of the ester. I know that these hydrogens are really acidic. They have a pK below 16. So I can just deprotonate there. We can then alkylate using an alkyl halide of some sort, usually alkyl chlorides, alkyl bromides, alkyl iodides. We've just made a carbon-carbon bond. And if that's the product you want, you can just stop there. You could add a second R group if you wanted to, because that hydrogen, again, is still acidic. But then I can take this molecule and I can place it in water with acid, and I can heat it up. What's going to happen? It's going to decarboxylate. I'm going to hydrolyze the ester and get a carboxylic acid because it's under acidic conditions, and then it's going to decarboxylate. And what's my product going to be? A ketone. So the acetoacetic ester synthesis allows me to synthesize ketones. The malonic ester synthesis allows me to synthesize esters. But in reality, the chemistry is almost identical. The only real difference is to decarboxylate here, I need to be about 55, 60 degrees usually. To decarboxylate here, it will decarboxylate even at really lower temperatures. So technically, heat could be room temperature depending on what's on the R group, okay, if it can stabilize the enol. But those are very difficult to isolate as the keto acids. They want to eliminate very, very quickly. Anybody tell me why there would be a difference? Why might that acid ester be more stable than an acid ketone? It does have something to do with the extra oxygen of the ester. That's absolutely true. So I leave that as something for you all to think about for Friday, okay? And we'll talk about that more on Friday. But malonic esters, acetoacetic esters, synthesis, pretty straightforward stuff. Allows us to do a lot of different things. So today we're going to talk about a couple more reactions. We're at that point in the semester where name reactions keep coming. And if you have trouble memorizing name reactions, that's going to be the difficult part for you. You've already learned all the mechanisms that I'm going to teach you this semester. You've been exposed to all the mechanisms we really need. Now we're just going to use those mechanisms using different substrates to get different products, and that results in different name reactions. So today we're going to talk about a reaction called the Claisen reaction. We'll talk about a thing called the Dieckmann condensation. We've already talked a little bit about the malonic ester synthesis, so we'll go through that fairly quickly if I still have those slides on here. And then the aldol reaction. Okay? So ethyl acetate, right, is a what functional group? It's an ester, right? And if I take ethyl acetate, which, by the way, is used as an emulsifier in food ingredients, and it's also used as an organic solvent. And I treat this with base. I actually form a new carbon-carbon bond and form a beta-keto ester, which was used in the acetoacetic ester synthesis, right? This is ethyl acetoacetate, and it's a beta-keto ester, okay? So you need 2 molecules of ethyl acetate to do this, and you form this product. Walk me through the mechanism. What do you think is happening? Which hydrogen? Okay, so those are acidic, right? So if the base removes one of those acidic hydrogens, what do we get? I get a carbon nucleophile. And I generate a lot of that carbon nucleophile or a little bit of that carbon nucleophile. What do you think? Do you think that these protons are as acidic as they were in the malonic ester synthesis? No, they're not. So we're not going to generate 100% of the enolate. But I've just generated a carbon nucleophile in the presence of an ester. The carbonyl of an ester, is it a nucleophile or an electrophile? It's an electrophile, right? So I just generated a nucleophile in the presence of an electrophile. That's a marriage made in heaven, right? And so what's going to happen? That's right. The nucleophile is going to attack the electrophile, and we're going to make a new carbon-carbon bond like this, okay? And so here's some examples, okay? This is called a crossed Claisen reaction. Why is it called cross? Back here, what was the identity of the two esters? We had two ethyl acetates. That means they were identical, right? The nucleophile and the electrophile are generated from the same ester, right? Here, however, they are different. We have one ester. Are there any alpha hydrogens on this? So can it generate an enolate? No. This is the only one that can generate the enolate, right? And so under these conditions, we generate a little bit of the enolate, and it attacks this ester, and we form this beta keto ester, okay? And so sometimes it is possible to carry out this reaction quite easily. Let's look at the mechanism in general of the Claisen reaction, and then we'll talk about the mechanism of the cross-Claisen reaction. So in the previous example, we had ethyl acetate. And I'm going to draw one of the hydrogens out separately just for convenience. So I've got a flask full of ethyl acetate, and Matthew comes along and throws in some base. And so now what happens? Okay, we're going to abstract the alpha hydrogen. I'm just going to draw it like that. There is. Plus ethanol. And of course, we've got a sodium ion around, right? Let's make everything balanced. That's the carbon nucleophile, but I can draw the resonance structure, right, where we put the oxygen has the negative charge. Okay? But I'm just going to draw this resonance structure for right now. But notice that they are resonance stabilized. Okay? Now, I generate some of this. Right? But in reality, the equilibrium lies this way. Right? Because this is actually a little bit of a stronger base than ethoxide. So I'm not going to generate a bunch of it. pKa determines that we're going to favor the weaker acid, weaker base pair. That's on this side. Okay? So I generate a little bit of the enolate. And in that flask, there's a little bit of enolate now, but a whole lot of ester. Right? And so what happens is, what? Attacks the carbon of the carbonyl. And I get what kind of intermediate? Tetrahedral. Now what happens? That's not the product, right? So what happens? How? Plus OET minus. And now what happens? I've got these really acidic hydrogens now, right? So the base that I just generated consumes one, and I generate an enolate. And that's where it stops until I quench the reaction by dumping it over water with a little bit of acid, and that gives it back its proton, right? And so it's this process right here that drives the equilibrium in this direction, because this deprotonation is very stable. You got all this resonance delocalization. So we generate a little bit of enolate that immediately reacts with the remaining ester, and you can form these beta keto esters quite easily. Okay?
More like keep adding argon like we were doing earlier with the acetoesters or whatever. Could you keep going? Could you have what you have there?
I could do this and let it run until it gives me all this, and then I could dump in, say, iodomethane or something and make a new carbon-carbon bond there. Yeah, I could do that. Because that would just be the next step in the acetoacetic ester synthesis. All right. Sure. Start over here. So now in the crossed Claisen reaction, we need to have an ester that can function as the electrophile and only as the electrophile. And we need to have an ester that can function as the nucleophile. So, what's going to happen? It's going to abstract an alpha hydrogen. You're starting to see a theme here, right? We're going to abstract an alpha hydrogen. I'll just draw in one of them, right? And so we get an enolate, a little bit of that enolate, and now it reacts with the other ester that's present that can't generate an enolate. And I'm not going to draw in all the mechanism because it's the same as over there, but after that we get the product. It is very, very important that you have one ester in a cross-Claisen reaction that cannot form an enolate. Okay? And let me give you an example. Let's suppose Aubrey comes into my lab and he wants to react this ester with this ester using the base sodium methoxide, and he wants to make this beta keto ester. That would be a crossed Claisen reaction. Why is he going to fail miserably? Pardon? Both have alpha hydrogens, and why does that matter? They can both be nucleophiles, and they can both be electrophiles. Two different products? Let's say if this is the nucleophile and this is the electrophile, right? He would end up with this product, where this was the nucleophile, this was the electrophile. Does everybody agree with that? That's product one. If this is the nucleophile and this is the electrophile, he ends up with that product. That's product number two. But he can also have a situation where this is both the nucleophile and the electrophile, which means he would get this, and this can also be the nucleophile and the electrophile, which means he would get and they would be about more or less 1 to 1 to 1 to 1. So at best, he would get 25% yield. Then you got to figure out how to separate it all. You would hope that maybe one of them would be a solid, a couple of them might be liquids, you could distill. It would be a pain in the butt, right? So doing these types of crossed Claisen reactions like this are impractical unless what? Okay, well that's true. If we have one that has no alpha hydrogens, we're okay. But what if he really wants to do this? And these are the only starting materials I have in my lab, and he needs this product or he's not going to graduate. How does he make it happen? What would I protect?
Any way to get rid of those alpha hydrogens on either one of those.
Okay, so that's not a bad thought. Have we talked about ways to protect hydrogens? Not on carbon anyway, right? We can protect hydrogen on alcohol by making it an ether, but that's not the situation we have here, right? He has to find a solution to where only one of those behaves as a nucleophile and only one of them behaves as an electrophile. How can he solve this problem? I could use temperature. I could use really low temperature. That's going to be part of the solution.
Possible to swap those hydrogens out for like a bromine or something on one of them, and then take bromine off later? Because then you have the alpha hydrogens on that one, and then they could react, and then the bromine can take it back off.
I might be able to do that on paper, but I'd still flunk you for it. It would be a lot of steps. Temperature is involved, I'll give you that. Solvent's going to be important here. Polar aprotic, low temperature, strong base. In the past, we've been using a weaker base, right? And we didn't generate a lot of the enolate. I need to generate 100% of the enolate, so it can't function as the electrophile, right? So what Obry would do, he wants this one to be the enolate, right? The nucleophile to attack here, because that's where this group comes from, right? So what he's going to do is he's going to take a flask, and in that flask, if I can draw it badly, he's going to put something like THF and LDA, which is a strong non-nucleophilic base. And he's going to take that flask and he's going to place it in a bath of dry ice and acetone, which will get him to minus 78 degrees Celsius, really cold. So we're in a polar aprotic solvent. We've got a strong non-nucleophilic base, and we've got really low temperature. And he's going to take this ester, and he's going to put it in a syringe with a little needle, and he's going to add it dropwise, really slowly, so that the temperature doesn't increase. And in doing so, he's going to generate that enolate. And only that enolate is in there. That's all he can generate. He hasn't added the other ester yet, so it couldn't generate an enolate. And so while this is at really low temperature, after he generates this enolate, then he takes another syringe and adds in this really slowly, drop by drop, meaning that it's the only thing around that can function as an electrophile. And he can get this product in reasonably good yield, probably around 85%. This is called a directed Claisen reaction, where we are forming 100% one enolate under very strong basic conditions so that we don't have an equilibrium. We completely form the enolate, we drive that reaction to the right. That's all that's in the flask, and then he adds whatever he wants to be as electrophile. So yes, there are solutions to the problem, but this starts to become more technical. Well, this is kind of a pain, but it's a lot easier than replacing hydrogens with bromine and then doing all that kind of stuff, right?
Is it still crossed?
It is crossed because we're using two different esters. It is still a crossed Claisen reaction, but it is directed. We have taken one of the esters and completely transformed it into the enolate, okay? The other Claisen reactions, we were taking the esters as a mixture, right, and running it at the same time. Very convenient. You guys will do something very similar to the Claisen reaction in the lab called the Schmidt reaction, or the Claisen-Schmidt reaction, and it's so easy. You mix the two components together, you throw in a single bead of sodium hydroxide in ethanol, and out falls your product. And you filter, you wash, you dry, and you're done. I don't know when it is. But each and every one of you will get product in that lab, okay? You will get product in that lab. It just cannot fail. And if it fails, then something happened, right? So we have this idea of a crossed Claisen reaction that can be directed or a situation where we have only one of the esters having alpha hydrogens, both of which are fine. All right, let's look at some problems that you might find on a standardized exam. What would be the major product of this reaction? Now, don't answer it quite yet. What is the name of the reaction? That's going to be a Claisen. Is it crossed or not? It is not a crossed Claisen. What do we know that a Claisen must give us? Beta keto ester. That needs to just pop in your head. I know a Claisen gives me a beta keto ester. Can I eliminate anything based on that information alone? I can eliminate D. I do not have a beta keto ester, do I? Right? Can I eliminate anything else? I can eliminate A. That's not a beta keto ester of any kind of how you do it, right? So if you were running low on your exam time, whatever it is that we take the exam, right? Because you know that a Claisen reaction gives us a beta keto ester, you've just eliminated two possibilities. You went from a 1 in 4 chance of getting it right to 50-50. And as I've said before, if you're at the casino, 50-50 odds, you start laying down lots of money because you're going to go out the winner, right? So, given that, what's the correct answer? Do they look the same? To you, they do.
Well, C has an extra option.
Hmm? Not which? Why is it for sure not A? This isn't a beta keto ester. It's a diester. Right? B is the right answer. Because for this to be the right answer, Yusuf, that means that the ester would have had to generate the enolate here. We don't generate the enolate on this carbon. We generate the enolate on that carbon. Right? And so we would have had to generate the enolate there to do the chemistry. So B is the right answer. Good test-taking skills will get you far in life. What would be the major product of this reaction sequence? Now ask yourself, what kind of reaction is it? It's a cross. So we know that one of them is going to function as the electrophile, one of them is going to function as the nucleophile. It's still going to be a beta keto ester, so can we eliminate anything based on that? We can eliminate D because it's not a beta keto ester. What else can we eliminate? Alpha, beta, yep. We can eliminate A. What else can we eliminate? Well, we've eliminated 2 for sure, right? B is the right answer. Actually, you can eliminate C as well, right? Notice on these questions, did you have to work out the mechanism? No. You had to know the very fundamental part of a Claisen reaction gives me a beta keto ester, right? And you could have you eliminated on that at least 50%. That's how this exam goes. Okay? People always tell me, "Oh, it's the hardest exam I ever took." It's not really. You can eliminate half the answers every time on this exam, I promise you. Okay? For the most part. You can eliminate half the answers if you know that fundamental part of a Claisen reaction gives me a beta keto ester. Yes, ma'am. Okay? That's not a dumb question. So the ester, right? This is the alpha carbon. That's the beta carbon. And on that beta carbon is a ketone. So it's beta keto ester. Let's see, alpha, beta. That'd be a gamma keto ester. which is not a Claisen reaction, right? Why is C wrong?
C we're using the left one as the nucleophile. Because of where the ester is.
No, it would have used this one again as the, wait, let me think about this. No, you're right. Yeah, we would have had to generate the nucleophile there. And then, and that just, those aren't acidic. You tell me. If we look at this one, there's no alpha hydrogens, right? This is a benzene ring. So there's no alpha hydrogens. This one has the alpha hydrogens. Let's look at this one. Which of these reactions would be used to prepare this beta keto ester?
We're going to have number one.
Hmm? Technically, Aubrey, you're almost right with one. The problem is you would need another step. This could generate the enolate, which would then give me the beta keto ester. But then I need base again to deprotonate that to get and then react with this. So just doing this and then dumping in that will not give you the product. This will, because you generate the enolate here, and you do a cross Claisen. Here, you're generating the enolate of a ketone, and you're attacking a carbonate. One of these will function as a leaving group, and the other one will remain. And so you could get there. That's not what you traditionally think of as a Claisen reaction, but it would still get you there. The Dieckmann condensation is another name for a Claisen reaction that just happens to be where the two esters are connected together. So back in the day when organic chemistry was in its infancy, a person found a reaction and then did it just a little bit differently and they got their name stuck on it. Okay? You will not find a reaction with the name Masterson reaction. It doesn't exist. We're out of names, right? Pretty much. All right? Well, we're out of, we don't really do new stuff like this anymore, right? I mean, I use this to do other things now, to make materials and make compounds that we want to study in biology and that kind of thing. So the fundamental organic reactions have pretty much so been done, right? So if we look at this, this is nothing more than an internal Claisen. One of the alpha carbons is going to function as the enolate. One of the carbonyls is going to function as the electrophile, and you just do a Claisen reaction, and in the process you form a ring. In this case we form a 6-membered ring, so we're going 1, 2, 3, 4, 5, 6, right? Which carbon, 2 or 6, is functioning as the nucleophile, as I have them numbered? Six is the nucleophile. 6 is the nucleophile because I have a 6-1 carbon-carbon bond, right? Carbonyl 7 is still an ester, so it couldn't have been the electrophile, right? And so we formed a nice 6-membered ring. About 80% yield. What do you think the mechanism is here? The same as the mechanism we talked about before, except you've got carbons connecting the two esters together, and that's why you get a ring. Nothing new, right? You just need to know that a Dieckmann gives you a cyclic beta keto ester, right? But nothing new. Nothing new in terms of mechanism. What is the starting material that will yield this compound upon treatment with sodium methoxide in ethanol? Counting carbons is very important. It is D. So tell us how you arrived at that. What was your thought process? All right. We know we've got, in all cases, we've got diesters, right? Now, I would have argued we could have eliminated one right off the bat, and that would have been B. Because notice we've got an ester and a ketone. That's not what we need. So I could have eliminated that one. The others are all diesters. And so basically what you got to do is count the carbons in between, right? So I know that this is 1, 2, 3, 4, 5. That's going to make the 5-membered ring. If I generate the enolate here and it attacks there, that will give me the 5-membered ring. If I did it on this one, right, I would get a 1, 2, 3, 4-membered ring. Here I would get a 1, 2, 3, 4, 5, 6-membered ring, right? And so this is a way in which we can make carbon-carbon bonds and rings. What other reactions have we talked about that form rings? Diels-Alder. The Diels-Alder makes 6-membered rings very well. The Dieckmann cyclization can also make 6-membered rings, but it can also make 5-membered rings, and it can make, under certain conditions, 4 and 7-membered rings. Okay. Which compound, when treated with sodium methoxide, followed by neutralization with acid, will produce this beta diketone? We haven't talked about beta diketones, but you have everything in your toolbox to make this happen. What think you all? C is the correct answer. What would happen if B was the right answer, or if B was reacted? You would generate an enolate. That would attack here, and you would end up with a tertiary alcohol. You'd get a keto alcohol. There's no leaving group here. Here you generate the enolate, because that's the only place that has alpha hydrogens. It will attack here, give you the tetrahedral intermediate, which then collapses and you lose the methoxide. And so that would give you that beta diketone. Now, somebody asked about D. D would have made a ring here, and that would have been a 4-membered ring. That would have been very, very difficult to make. And it wouldn't have given us that, right? And this would have hung off the end. You got to step back and think. We've talked about the malonic ester synthesis. I'm not going to go through that, those 2 slides, because we already talked about that. So here's an example of a malonic ester synthesis that has proved fairly useful in our group. At one point, we needed to make this carboxylic acid. You start off with this stuff right here. This is called diethyl malonate, because the ethyl groups and the malonic ester, of course, so it's diethyl malonate. This stuff is dirt cheap. It actually costs more to ship it to you than it costs to buy it. Okay, so really you're paying for the bottle and the shipping, and they give you the compound for free almost. You react this with a base like sodium ethoxide, because that's the salt of this ester. You end up generating the enolate. This then does what type of reaction here? This is an SN2 reaction. We form the new carbon-carbon bond that we want. We now have this. We heated it up in mild acid and heated it up with some water around. We hydrolyze the esters to the acids. That then decarboxylates, and we end up with this carboxylic acid. Well, malonates are, there's a, where's my, what did I do with my, oh, right there. In nature, you will find an acid in some that is malonic acid. That's its name. And so if you make an ester of it, then you call them malonic esters. That's where you get the name from. Why did they call it a malonic acid? I have no clue. Okay, but what is expected from this reaction sequence? Draw it out. You'll have a blank piece of paper on the final exam. It is. You have 2.5 hours. 70 questions. ACS says you should only have 90 minutes. We give you the full 2.5 hours. Not A, maybe A. I'm hearing a lot of grumbling. What do you think it is? Not what? Definitely A? It is definitely A. It is definitely A. I want you all to work through that mechanism on your own tonight. But the cool thing is, we're making a 3-membered ring. What do you know about 3-membered rings? They're fairly unstable. But through this malonic ester type synthesis, you can make 3-membered rings. You can make 4-membered rings. You can make 5-membered rings. You can make 6-membered rings. It's fairly versatile that way. Okay? If this steroid, tetracarboxylic acid, is heated, which carboxyl group will be readily lost as carbon dioxide? It is the carboxylic acid at C2 because this is a beta-keto acid. The acetoacetic acid synthesis, or acetoacetic ester synthesis, remember I mentioned that those decarboxylate very, very quickly, right? There is nothing beta to these other acids, so they're stable. You can heat them up and they don't decarboxylate. Now, if you heat them up to like 300 degrees, yeah, they'll decarboxylate, all right? But this is the one that will decarboxylate pretty close to room, just above room temperature. Okay. What is the product of this reaction? B. So think about that one too tonight. We'll talk more about them on Friday. We're done for the day. Have a good afternoon, morning and afternoon.